Hello, hello. I hope everyone is doing well today. Today we're going to look at sketching curves using derivatives. We actually started off methods by sketching quadratics. So we had either happy faces where we had minimal because it was minimal worries, or it was a sad face where it was a maximum because it was maximum worries. We also had these turning points. We then looked at sketching cubics, which had either like up flat up or down flat down. And then we had these points of inflections. Now, we can summarize all that into stationary point. So a stationary point is a point on the graph where the function momentarily stops rising or falling. In other words, it's the point where the gradient is 0. So if we look back at our quadratics, our happy faces or sad faces, our stationary point would then be our turning point, because that is where, if we drew a tangent line, our tangent would be flat, horizontal. That's where it has slope 0 or gradient 0. So similarly, if we looked at the maximum quadratic, if we drew a tangent to the curve at that point, it would be a flat horizontal line. And similarly, the point of inflections, we would have the flatness where it changes from up to up again. So these turning points or these points of inflections, we call them stationary points because that is where the gradient is 0. And so we know that gradient means derivative, so dy dx. So to solve or to find these stationary points, or turning points or points of inflections, all we have to do is to differentiate our function and then set to 0 and solve them. So that's essentially what this box down below is telling us. That to find any stationary point, all we need to do is set our derivative f dash to 0, so that at those stationary points, at those turning points or points of inflection, the gradient at those points is 0. It's a flat tangent line. So then we have 4 different types of stationary points. We either have a maximum, a minimum, a up flat up, or we have a down flat down. So how can we tell apart these 4 different types of stationary points, aside from just solving like where the point is by setting the gradient to 0? So what we need to do is look at what happens near, a little bit to the left and a little bit to the right of each of our stationary points. So say, for example, we're looking at case number 1, we've got the sad face, the maximum. So we know at the point, the stationary point, the gradient is flat, it's 0. But if we looked at a little bit to the left of the graph, so if we looked at the graph on the left, if we drew tangent lines to that graph, we would have positive gradients because it's pointing upwards. And if we looked a little bit to the right of the graph and we drew tangent lines going down to it, then we would get negative gradients. So if we looked at a little bit left and a little bit to the right, we get a positive, flat, negative type of gradient pattern. Then we know it's got to be a sad face, it's got to be a maximum. And similarly, if we look at the minimum type, so at the point, at the stationary point or the turning point, we know the gradient is 0 because it's flat tangent there. But if we looked at a little bit to the left of the graph, tangents will be going downwards, so we know that the gradient would be negative. Versus a little bit to the right of that turning point, we have positive gradients because the tangent line is pointing upwards. And then if we look at the 2 different point of inflections, so at the point of inflection, we know the gradient's got to be 0, but a little bit left, it's going to be positive because the tangent's pointing upwards, and a little bit right of that stationary point is also going to be positive because it's pointing upwards. But in the final case, the 4th case, we have negative gradient, then flat at the point of inflection or the stationary point, and then going downwards our tangents, we would have negative gradients again. So to solve for stationary points, we need to differentiate and set to 0 because stationary points are where the gradient of the tangents is 0, it's flat. And then if we look at a little bit to the left, the gradient nature of the left of the stationary point, and then if we look a little bit to the right of the stationary point and check whether the gradient is positive or negative, we can then determine the types of stationary point we have. And there's 4 possible cases. Either we have a maximum, we either have a minimum, we have a inflection on a rising curve because it goes up, up, or we have an inflection point on a falling curve because it's falling down, down. Now this method, I call it the table method because usually we draw up a table of values checking points a little bit to the left and a little bit to the right of our stationary point. There's also another test called the second derivative test. It's not always that useful, but it is much faster than this table method. So to apply the second derivative test, what we need to do is we need to differentiate twice, so find f dash dash. Once we find f dash dash, we can check the nature by looking at whether f dash dash is positive or negative. So if you differentiate twice and you put your stationary point value in, and if you get f dash dash is negative, then negative means sad. Sad means a maximum. If your second derivative f dash dash is positive, positive means you're happy, happy means your minimal worry, so your happy face, then we know that it's a minimum. But the problem is, if your f dash dash is 0, well, we can't really tell what kind of point of inflection it is. It could be either a rising or a falling one, in which case we then have to revert back to the first method, the table method, to check. So second derivative test is fast if we have a minimum or a maximum, but if we have f dash dash being 0, we still have to go back and have a look at a little bit to the left and a little bit to the right of the point, stationary point itself, to see the nature of the gradients, to then test whether we have positive positive or we have negative negative style.